Good afternoon, everybody. I hope you guys are having a wonderful day. I'm going to do our first podcast here on chapter 14 on intermolecular forces. And this is going to be a very quick chapter. We will probably be having a test in like 5 days. There's just a little stopgap here between a couple of our chapters that we are doing. So first thing is called intermolecular forces and phase changes. Now, intermolecular forces probably don't mean a lot to you, but hopefully a phase change does, in that we're going from a solid to a liquid, liquid to a gas, or back down, and we're going to draw a phase diagram here of that in just a moment. So intermolecular forces, they're attractive forces that occur between molecules. We're going to be talking a lot about water in this chapter, so let's just draw our molecule of water as we studied a few chapters ago. And we figured out in this water molecule that this side is slightly positive, this side is slightly negative, and this side is slightly positive. And if you recall, we talked about those electronegativity forces, and electronegativity is greater for oxygen, and so that's why it has the electrons pulled a little bit closer. So what this force is, we've talked about this already in class, about that little bubble, that surface tension that water makes when it attracts to another water molecule. So if I draw another water molecule in here, and again label that this side is slightly negative and the other hydrogens are slightly positive, I would hope that you're thinking, well, I have a positive and a negative. I bet there's a little bit of attraction there. And you're exactly right. There's going to be a little bit of attraction between that hydrogen and that oxygen. That is the intermolecular force. What is the force that occurs between molecules? So a simple little way to remember this is that you need to think about our interstates. Our interstates are roads between cities. So those roads between cities that connect our nation, and that's an intermolecular force. It's that force between the molecules. Think of it as the roads between cities. Then we conversely go to the other side and we talk about intra. So you can see that this is intermolecular, and then we have intramolecular, and those are the attractive forces that occur between the atoms. So if we keep the same scenario going, this would be our roads within a city. What is connecting my house to the high school or your house to the high school? That would be the intramolecular forces within a molecule. So if we think of Hastings as a molecule. So an example that I have here, we could use water again, which would make the most sense because I used it in the last example. And this is, again, slightly positive, slightly negative, slightly positive. That's not going to change. So the intramolecular forces is this force. What is that force holding that oxygen and hydrogen together to make the molecule of water? Where the intermolecular is the forces between the molecules. So we'll be studying more of that in this chapter. And then we're going to talk about this bond continuum and all this, how different compounds are being made. We've talked about metallic already, C of delocalized valence electrons. And again, this is just what makes aluminum, and copper, and nickel, and all the different metallic elements that we have here on the periodic chart. All right, looks like I have some drawing on here from another podcast. So again, this would be aluminum and copper. So then we have ionic bonding. It's a transfer of electrons, usually between a metallic cation and a non-metal anion. And I think the most common one that we've talked about all year long is NaCl, metal to non-metal. Then we have covalent bonding. And so we have seen this slide before. We are just trying to add some more terminology to it. And this one is going to be, these are the intramolecular. So within the city of Hastings, within the molecule, can I say if it is polar covalent or non-polar covalent? And remember, we talked about winning the tug of war on one side or the other, if they're equally shared or not when we are drawing all of these molecules. Then this is where we stopped. We stopped before showing that it was either polar or non-polar, and that was a couple chapters ago. Now we're going to add intermolecular, meaning how do they bond within between the molecules. So we have hydrogen bonding, like water is a very good example here. We have dipole bonding, hydrochloric acid, we have used that in class. And then London dispersion forces, that hydrogen gas that we just collected in a lab last week displays this type of force. So I have separate slides for hydrogen bonding and LDF, so I'm just going to talk about dipole-dipole here. And if I draw my HCl, hopefully you would remember that we drew hydrogen with one bond between the H and the Cl. And if we look up at the periodic chart, you should be saying that chlorine is closer to fluorine. Remember, we talked about that fluorine is so attractive, that crazy little clip that we saw. And so this side is negative and this side is positive. So what this means is that when I draw the next hydrogen and the chlorine coming in, it is going to be like this, and there's going to be attraction between these two because of the opposite charges that you have there. So this is called a dipole moment. Now, there's different strengths with all of these, and I would say that you could use a numbering system. Hydrogen bonding has the strongest, then dipole bonding would be the second, and then LDF is the weakest. So that's how it goes in terms of strength of bonding. Maybe you want to write the word weak over here so you can see that. A weak bond, and this is going to be a strong bond. Okay, so the hydrogen bonding I showed you that day on the tabletop when I put water on the tabletop and then I burned that ethanol on top of it. That was the difference in the type of bonding that we had. And so for hydrogen bonding, water is unique and special. We've talked about that all year long. It's very polar, and it has a positive end and a negative end that we have just discussed. So we have a positive end and we have a negative end, and then there's many attractive forces there. And this is what causes many of its unique properties, that ice floats in the liquid form, that it expands as it freezes, that it's able to dissolve many, many substances. Now, this hydrogen bonding only occurs with fluorine, oxygen, and nitrogen. And so a way to remember that, the movie buffs in the room, phone home, meaning fluorine, oxygen, nitrogen bonding with the hydrogen. So if you could think of that movie, that would be E.T. If you're thinking that, you're correct. And so if I have HCl, chlorine is not one of fluorine, oxygen, nitrogen, so that would not be a hydrogen bond system. Okay, then London dispersion, or we'll call them our LDF. And we talked about that these are really weak. They're very weak forces that exist between nonpolar molecules. So the methane that we have in the room, or the alcohol that I put on the tabletop, you could smell it right away the minute you open it. That is going to be something that has a weak bond between it because it breaks apart very easily, and then we can smell the scent. And so these LDFs, they might have a temporary dipole. We're really not going to worry about this part at all. We just know that they are very weak and they are nonpolar molecules. And we'll be doing a lab on that so that we can study that and see that in front of us. Okay, then water phases and changing phase. And we've talked a little bit about this already, so that's why I keep saying that this is really a chapter that kind of mirrors a couple other ones that we've been doing. If we heat water at a normal boiling point, and you should be thinking that our normal boiling point is 100 degrees Celsius here in Hastings, Minnesota, temperature at which the vapor pressure is equal to the external pressure. So we talked about this in the gas chapter, that we want to be able to have things evaporate and have things boil. And so evaporation, if we think about that, you can look at this picture. It's a very good picture in that this is only happening at the surface. So the water molecules are leaving the surface here, going from a liquid to a gas. When I go to boiling, you guys can see that there is bubbles underneath here. And so they can overcome the pressure. You guys saw me do this with the vacuum chamber the other day. And so these molecules can come out of here. So this is going to happen below the surface. So it's going to happen below the surface. Now, am I still having evaporation at the surface? For sure. So for this one, I could say that I have evaporation at the surface, I have boiling below, but this one over here, I can only say that I have evaporation at the surface. And we've talked about how we can decrease that boiling point as we go up in elevation. And here's the example that I have here. We talked about how in the vacuum chamber I removed all of that pressure and I was able to get it to boil. So cooling water, you guys can read that. We've talked about this before. I'd like you to go to this slide. This is what we're going to be doing in lab. So let's write degrees Celsius over here. And then on the x-axis, we're going to write delta H. And hopefully you're remembering that that is our change in heat. And then we're going to draw a heating and cooling curve. And we're going to do this for water. So up from the top, I'd like you to write 0 degrees Celsius. Don't put that at the origin like we normally do. And then 100 degrees Celsius. And so this is going to be for water. So if we make our cooling curve, or heating, we're going to do our heating curve, but it'll just be the exact opposite when we cool in the other direction. If I'm starting right here and I'm heating it up, it should make sense to you that this is going to be ice. So this is going to be a solid, okay? And it's heating it up and heating up, be the ice molecule like we always talk about, and that the particles are going to be barely moving. And so this is going to be kinetic energy, energy of motion. Then all of a sudden at 0 degrees Celsius, you would see that the temperature isn't going to change and it's going to plateau. This is going to be our potential energy. And this is when the molecules are gaining more energy, gaining, and then all of a sudden they're like, all right, I need to change my phase. And they're going to increase in kinetic energy again. And now this is going to be my liquid. So now to get another phase change again, I have to have a gain of potential energy. So it's going to stay at this temperature for a short amount of time. It's going to gain some potential energy. Once it has enough, then I can change my phase again. So now I have a gas and I have kinetic energy again. So like we've talked about that bouncing ball. The bouncing ball, when it's sitting at rest, has potential energy. It falls, it's kinetic, and then it rests again, and that's potential. Water and other substances that go through phase changes do the same thing. Kinetic, potential, kinetic, potential, and kinetic. And this is what we're going to do in lab. You guys are going to all ask the question, well, Miss Benson, the temperature's not changing when we're back in lab. And I'm going to shake my head and smile and say, yep, that's what we're looking for. So we want to see these phase changes. Then we know that that's the temperature that the substance is going to change its phase, go from ice to a liquid or a solid to a gas. So that's what I have for you today. You guys should be working on your book questions now. Let me find the page for that. So page 497, I'd like you guys to work on 1, 4, 5, and 6. All right. I hope you guys have a wonderful day, and I can't wait to see you tomorrow in class.